Hello and welcome back to this series of lectures on integral calculus. In this lecture I will present some key aspects and some examples on the method of change of variable. Now, if you're looking at this screen, you may be wondering why the chain rule? I hope, by the way, that you have recognized that formula as expressed in the chain rule. Well, because the chain rule is in fact behind, and it's the motivating force behind this method of change of variable. More precisely, here is why. Now, let's start to develop this method. Of course, we're going to start from the chain rule itself. Remember, the chain rule says if you're taking the derivative of a composite function, one that has an outside and an inside, what you do is you take the derivative of the outside, keeping the inside fixed, and then multiply that by the derivative of the inside. If you're still not sure about the chain rule, you might want to review it, but I'm sure you are at this point. Well, every time you have a formula for differentiating a function, you automatically end up with a formula for integrating another function. All you have to do is reverse the formula. So once we start from that formula, if we reverse it, we end up with this. Great, lovely looking formula. Except, what are we going to do with it? This looks quite confusing, doesn't it? Well, there are a couple of things that we can do, and we're going to see all of them. And in fact, we're going to see the main method in just a few minutes. But we're going to start from the easy case. What is the easy case? Well, the easy case is when we look at an integral and we realize that yes, it does come from a chain rule. So in other words, that strangely complicated formula inside the integral sign, that integrand that we're looking at, pops up to our mind as being the derivative from a chain rule. And therefore, we're going to draw conclusions from that. Probably the best thing to do is to give an example. Let's say I ask you to integrate that formula, particular function, 2x cosine of x squared. Well, here you might say, oh, wait a minute. I can see that the x squared is my g of x, is the inside portion, and the 2x is just its derivative. 2x is the derivative of x squared. That leaves us with just the cosine, which of course is going to be our f prime. And what is cosine the derivative of? Well, sine, of course. So we can unravel this integral as being simply the integral of sine of x squared. If you're not sure, we can take the derivative of sine of x squared and realize that it is in fact 2x cosine of x squared. Oh, of course, don't forget the plus c. But what if the pattern is not as clear? I mean, this was particularly simple and particularly clear. Probably you would have been able to do it before I gave you all this spiel. But what if things become a little bit more complicated? That's where the method itself comes in. So let's see how this change of variable actually becomes a true method with its steps, and it's a method that is very, very, very useful. First of all, we start still from a situation where we look at our integral and say, that gives me the feeling that it's coming from a chain rule. It smells like it. I may not be able to recognize the pattern in full, but it smells like it is coming from a chain rule. Maybe all we were seeing is a composite function, something that has an inside and something else that looks somewhat like an outside. So we have a vague recognition that it might be coming from a chain rule, but we're not sure. Okay, so what are we going to do? First of all, we're going to rewrite the integrand if needed or useful. Remember, this is always the get ready step that we want to do at the beginning. Maybe we may want to simplify the function itself, rewrite it differently, or whatever. Secondly, we're going to identify a potential inside function. Remember, this comes from a chain rule. There's going to be an inside and an outside. So we're going to identify that inside function, and we're going to call it u. So u is going to be our new function. So that corresponds to the g of x inside the formula. Now, next, what we're going to do is we're going to properly compute its differential. Remember, the differential of a function is going to be given by the product of its derivative times the differential of the original variable. So you can think of u as a function of x, or you can think of u as the new variable. That's why we call this thing the change of variable method. Okay? Now next, what we're going to do is we're going to use this formula we found relating differentials to figure out what dx is in terms of du. So the general formula is that dx is going to be equal to du divided by g prime of x, and in each particular situation it will be something different. Next, we're going to rewrite the integrand and the differential in terms of the new variable. So we're going to change, as the name says, we're going to change the given integral to a different formula which will involve u instead of x. Okay, so we're gonna hopefully end up with something that looks like this: integral of some derivative of a function of u in du. Now at this point, if only the new variable is present, we're going to compute the new integral. Assuming, of course, we know how to compute it. Assuming that the method is going to work. We're going to come back to these assumptions in a minute. So this will give us an indefinite integral of the form capital F of u plus c. And now all we had to do is the last step, which is of course switch back to the original variable. Remember, we introduced this variable u as a tool, as an auxiliary piece of information to allow us to compute the integral, but we had to go back to our original variable. So all we had to do is change u back to g of x, which is what it was to begin with, and hopefully that will give us the answer.